Are you ready? Yep. Okay. Show me that you're ready with the chit chat stopping. All right, cool. Can you guys see that okay? Should I make that a little bit brighter? Make that a little bit brighter. That looks a bit better. Okay. So, what we are looking at is part B of our titration assessment. So basically, we've done our first part. We've collected our data. We've made a method. I'm just trying to think what's the best order for me to kind of explain this to you guys. Okay. I'm going to dive into it first and then talk about the marking schedule next. Okay. So, ladies that are doing science. All right. So, one of the things we have to be mindful in this titration, let me just kind of give you an overview of what you've done so far. So for part A, remember you did a rough ratio. So you took your pipettes and you basically figured out how much base do I need for my acid. So if you had 1 ml of acid, say for example, some of you guys figured out that you needed like 14 milliliters of the base. Is what you guys did in your first step. After you guys did that, what you then did is you proposed a dilution method. And you took an aliquot of that dilution. Are we okay so far with where we were? Yeah? All right. So there is also part B and there's part C. So let me kind of run you through the ideas between part C and part D. So part B and also part C. I'm actually going to jump to part C and then backtrack why we need to do part B. So when you guys have part C, what you are doing is you are taking your diluted solution and you're going to use that for a titration. So you're going to have your diluted unknown solution and you titrate it against the known concentration of your base. So that's what you guys are going to be doing in part C. You guys are going to be collecting the data and analyzing it. We good so far? All right. Now, something to keep in mind before you do this titration is we want to double check the concentration of the base. So that's what causes us to do part B. So basically, before I do part C and I do my titration, I just want to double check that this concentration is right. So you're basically adding another layer in your accuracy and precision because now we can verify multiple layers to make sure whatever we're using is correct. So that's what part B is. We will often call this solution here that you're using and that you're double checking in part B your primary. Standard solution. So just keep that in mind. What we're then going to do is we're again doing a titration. I'm just trying to find where my little to-do list went. There we go. That'll work. All right, so to double check my base concentration, I will titrate it against a different acid. let's see, stock sample. Yep. So this one we refer to as our standard solution. This is our first one. So basically, we're just double and triple checking ourselves when it comes to this. Your unknown solution in this case would be called your secondary. Just in case any words pop up and you're not sure what they're referring to. So secondary is what we are trying to solve for. Primary is what we're going to be using, but we need to double check our primary against the standard solution. Again, this one's going to be a titration experiment. The only difference is with part B is that I give you the data instead. The part B and the part C calculations are more or less identical. There are a few steps that will be slightly different, but you're using the same kind of technique. Are we okay with that so far? All right, shall we start looking at the B question? All right, so now with that in mind, let's look at what we are doing for part B. So part B, I want to double check my sodium hydroxide concentration. That's what I'm going to be using for the titration, and that's what you guys used in part A as well. So it cannot accurately be used unless I carry out an investigation to check its standardization, and I'm checking it against sulfuric acid. So sulfuric acid is what I'm going to be using as the neutralization reaction. What I've also been given is the balanced equation, so that way if I know my concentration of the sulfuric acid, I can verify the concentration of the sodium hydroxide. So that's what we're looking at so far. Now the steps that we talked about on Friday are going to be applied for today's lesson. So first thing I need to do is I need to make the sulfuric acid, and that's why it's my standard. Because I have produced it, I can be confident about the concentration that it is. So some things to keep in mind is that I have hydrated sulfuric acid. So the sulfuric acid does have a little bit of water mixed into it, and I have to factor that into my weight and things like that. So they say that I weigh out 1.79 grams of the sulfuric acid in a dry laboratory, and I add it to 250 milliliters of water. And then I shake it and it's fully dissolved. Now what I need to then do is calculate the concentration of this sulfuric acid that I made. So we're using those equations that we've talked about in the previous lesson. Now, I will color code things achieve, merit, and excellence. What I'm going to do is go through the full answer, and the full answer is at the merit level. And then what I'll do is show you little tweaks to get it up to excellence, and also where the mistakes fall to get you down to an achieved. Okay? So first thing I need to do is figure out the amount. So remember that N equals M over N. And the other thing that they have given me is they've given me the molecular mass of the sulfuric acid that's hydrated. So I have my big M value over here. I have my little n value over there. It's worthwhile to go through and annotate it. The equation's already set up the way I need it. So I'm going to do the 1.79 grams divided by the 170.08 grams per mole. Are we good with that? I personally like to keep my units down just to make sure that I am doing things correctly. And I just checked my calculator was working for me. You guys can see that. So 1.79 divided by 170.08, and then that gives me the number in moles. I leave my answers unrounded. You want to round at the very end because having significant figures is part of the excellence. But I'm happy if you want, when you copy it down, just to leave it as a ... and not have to write down the full number. So that's how I'm leaving it. I know the number tail is longer. And that's in moles. We good so far? All right, next up. All right, next thing here is they want us to figure out the concentration of my sulfuric acid. So I'm looking for my volume. I already have the amount, and I'm using that from the previous question. So from question 1, I have my data. I do need to have the volume. The volume was stated up here. It was 250. Now I have to be mindful that 250 is in milliliters, so I need to convert that into liters. So what I need to do is divide that by 1,000. So that would actually be 0.25 liters when I do that calculation. All right, so let's plug in our numbers. That 0.10524 ... divided by 0.25, that's moles, that's in liters. That makes sure that I have moles per liter, so I've correctly put my numbers in the right place. Again, leave the numbers long in your calculator because then I can just do divide 0.25 and I don't have to worry about copying things down. So the concentration of that is 0.04209 or whatever you want to keep it. I keep it as, like I said, a nice long number. If you have those smarter calculators, what you can do is you can save them in your calculator as different letters. So like I think with mine from memory, I can't remember how I did it, but there's definitely a way you can save your numbers. All right, keep going. Okay, cool. So now I am going to be using my sulfuric acid, and I am using it in the burette and not burette, the pipette, and I'm aliquoting out a certain amount of that. So I am taking out 25 ml samples of my sulfuric acid, and then I'm going to use that to titrate against the sodium hydroxide. So again, we are using the value that we had in our previous calculation. In this case now, what I want to know is the amount of sulfuric acid in an aliquot. So that's the question that I'm trying to answer with this. All right, so I need to now rearrange this equation over here because this equation is solving for concentration, and I need to have it solving for N instead. So N is going to equal whatever my concentration is times the volume. Concentration I figured out from question number 2. Volume is going to be the aliquot. So the aliquot is what? 25 milliliters. Do I need to change it into liters? Yes, I do, because the concentration is in moles per liter. So if I was to divide that by 1,000, what would that be? 0.25. All right, so N is equal to concentration, which is 0.04209 ... That one is in moles, moles per liter, and then I'm timesing it by 0.025 liters. The liters will cancel out, and I will have the moles, so I know I've set it up correctly. So we'll take my calculator, I'm going to times it by 0.25, and I get 0.001052 with some long numbers behind. So I'm just going to do the same thing, 0.00105, and I'm just going to do lots of dots for now because I don't want to round too early. You'll see when it says to round. Happy with that? Concerns, comments, questions? Or keep going? Keep going? All right. Here's where the stoichiometry comes in. You're learning a new word today. All right. So they have given me a balanced equation. You guys don't have to worry about writing your own balanced equation. That's provided for you. And they say this is basically how much sulfuric acid you have and then how much in a ratio of the sodium hydroxide you need. You need to use these ratios here to calculate how much of the sodium hydroxide you need in order for the neutralization to occur. So for every 1 mole of sulfuric acid, I would need 2 moles of the sodium hydroxide. Are we okay with that so far? So if I had this number, am I going to multiply or divide by 2? Based on this ratio here. Do I need half as much or twice as much to neutralize this sulfuric acid? Twice as much. So times it by 2. So I'll take that 0.00105 ... times it by 2, and that's how much I would need in order to neutralize it. And again, I'm not rounding my answers just yet. You round at the end. But I am keeping my numbers long so that way I don't accidentally affect my values. So now we got that point. So double check your ratio. So sometimes with the ratios you might need to divide, other times you might need to multiply. It depends on what you're trying to do. All right, next page. Questions, concerns, comments? If you want to change to the other standard now that you've seen the amount of math that's involved, I am happy to switch you. All right. Now what I have is my titration data. This is, I'm just going to actually write down this full number because I'm going to, can I save it? How do I save? I'm trying to remember how I save my numbers now. Store as, I think I figured it out. Nope. Quit. Okay, cool. I figured out how to save the number in my calculator. All right. Now, this is what I'm saying for an example as provided data. When you guys do part C, this data is not provided for you. You guys have to practically find it. So the nice thing about part B is that it prepares you for part C. All right. What I'm looking at here is I need to figure out what the titrate volume is for each one of these titrations. So what you're going to do is take your final reading and subtract away your initial reading. What I am looking for is that you have 2 decimal places. So even if the number only has like 1, I want you to have 2 decimal places because the burette can read 2 decimal places. We take the next one, 34.03 minus 16.83, that's 17.20. So again, 2 decimal places. 18 minus 1.3 is 16.70, and then 34.9 minus 18 is 39. All right, so there are my numbers of my titrate volume. Right, what you will see that is something new on here is that they want you to calculate the average using concordant titrates. So concordant is a new word that you guys are looking for. It's basically looking for things that are within a good range. So if we're looking at the marking schedule and we're looking for what I'm saying with concordant data, I want a concordant range of 0.3. So what that tells me is that the highest value that I'm using as my data point minus the lowest value that I'm using as my data point is within 0.3 mils of each other. If they are greater than 0.3 mils, then I will limit myself and I won't be able to get an excellence or higher. I'll be stuck at an achieved. So let me show you what I mean by that. So what I'm looking for first is I'm going to look for my lowest value and my highest value just to see, do I need to eliminate any data? So looking at this is my lowest number. And then this 17.2, that's my highest value. Are you okay with that so far? All right, so if I do 17.2 and I minus 16.7, I would get the range of 0.5. So if I use this data without eliminating any data point, I will automatically limit myself to an achieved, because that data is not concordant. So what you need to then do is you need to eliminate one of the data points, either the highest value or the lowest value. So let's test out what our new high and low points would be if I use different data points. So let's say I eliminated this one. My new highest point would be this one here. So this is my new high, and that one would stay my low value. So if I use, this is my range would be 0.2 milliliters. That one's more acceptable. Let's just double check for sanity's sake, removing this one. So let's say you remove this one here, and then my new lowest value would be this one. So I would be doing 17.2 minus 16.83, and the range in this case would be 0.37. So is that one acceptable? No. So this one's not an acceptable range. This one that we did with all of our data points isn't an acceptable range. This one that we did here is an acceptable range. So what that tells me is that I need to eliminate data point number 2. And that's why you guys need to do repeats for your experiment. So you do your first trial, and your first trial is your rough trial usually. Yes, it's raining. So your first trial is normally your rough trial, and that gives you a ballpark idea. And then usually the 3 titrations that you do afterwards are more accurate. It is not always the case. If it's not, then you can always use your rough titration if it is within range. If this data doesn't look good and none of it is within a 0.3 range, do a 5th titration. Does that make sense? And that's why when we were talking about in part A, the number of titrations you can do is really important, because if you have bad data, if you can do 10 titrations or 25 titrations, you can still collect more data. If you're in a situation where you can only do 4 titrations because your aliquots are 25 mils and you've only made 100 mils of your diluted stock, then you're stuffed. Yeah? All right, so I'm going to take these 3 values as my average. So 16.83 plus 16.70 plus 16.90, and then divide that by 3 to get our average volume. Make sure you're watching what you're doing. Add all those numbers together, then divide. I've seen people do stuff like this and then do divide by 3, and they get a really weird number. Like 39 is not in the middle of those 3 numbers. Anyway, so 50.43 divided by 3 is 16.81. Now, one of the things you'll notice here is that it says including units and 3 significant figures. This here is now the excellent range, and it's really stupid that this is the excellence range, let me tell you. So when they say 3 significant units, what they're basically meaning is counting the numbers like from here onwards. So once you get a number, start counting. So this is my first significant unit, that's my second significant unit, that's my third significant unit. So I'm rounding to this number. And when I round that number, it would be 16.8. And that's what I would leave it as, and then milliliters. That's 3 significant figures. This here, if it's unrounded, that's 4. So that would prevent you from getting an excellence, which is really stupid. This one here is 4. That one here is currently 4. Any zeros after a number counts as part of your significant figures. So that's a 4, and that's 4. Do you want me to show you guys what another one is? Yeah? So like if I was looking at this guy over here, these zeros don't count towards my significant figure. It's only once we get a whole number, so a non-zero number. So this would count as my first number. That would be my second number. That would be my third. That would be my fourth. So what we're trying to do is round to 3 sig figs. So what I can do is go through and just kind of show you what it would look like for each answer. You wouldn't obviously do that on the actual assessment because you only need to do it when it states to do that. So if I was looking at here and I just wanted to know what 3 sig figs looked like, it would be, just an example. So right now this is 4. If I wanted it to be 3, it'd be 0.0021, and then that 0 there is my third number. I look over to the 4, I round down. So that's what that would look like as 3 significant figures. Do you want me to go through all the numbers and just show you each one? Just so you know what significant figures are. You only need to do it when it says to do it. If it doesn't say to do it, don't worry about it. So like this one here, if I wanted 3 significant figures, 1, 2, that's my third one. And then the 2, 4 would get dropped. So it'd be 0.105 if I wanted to do 3 significant figures there. This one here, 1, 2, 3, that's my third. The zeros in front don't count. The zeros after count, after the numbers. So 0.042, and then since this is a 9, that rounds up to 1. Sorry. Keep going. Oh, I didn't save this number in my calculator. Don't know if you were supposed to round up or down. I think you had to round up. We'll use this one instead. So those 2 zeros don't count. That is 1, 2, 3. Oh wait, I did that one before. Never mind. This one here, these 2 zeros don't count. That's my first, that's my second, and then if I wanted to get an imaginary third number, I would just add a 0 at the end. 3 sig figs. You're gonna hate it. It's a rule in chemistry. All right. I don't need you to do it though unless it says to do it. Otherwise, leave the numbers nice and long because if you round too early, it's gonna affect your numbers. Again, it's stupid, but it's something I would holistically forgive if everything else was right. All right, cool. So now that we have figured out the average titrate volume and we know the amount of sodium hydroxide that we use, we can figure out the concentration of my sodium hydroxide just to verify it. So we're taking 2 separate numbers. So we're taking the number from question number 4, which is this number here. So we're doing concentration is equal to N divided by V. So my N was question 4, this one here, 0.002104 ... mole. And we are dividing it against that number here. I like to use my whole numbers, 16.81. I lie. Remember, that's in milliliters, so we need to convert into liters, so 0.0168. If you want to use the unrounded number, I wouldn't be fussed. All right, and then we do our final answers. So I saved A to be our number, and then you divide it by your volume. And then that's our concentration. Whoa, quit. And that's our concentration of sodium hydroxide. So N equals 0. Oh, let me do it to the excellence level. So again, this one you have it pop up again. 3 significant figures, including units. So the last 2 questions that require it. So that would be 0.125. And when I see that 5 over here, that's my third number. And then I go to the next number, it's 2, so I round down. And then moles per liter is my final answer. So that's what my concentration is. In theory, it was supposed to be 0.1, so it's a good thing I double checked it because it tells me it's a little bit too high and I'm gonna have to dilute it a little bit just to make sure I have 0.1. Or I can use that number, whichever. All right, questions, concerns, comments? I know that sucked. Yes? Why do we divide that by 3? Because we added 3 data points together. 1, 2, 3. If I had kept all 4, I would be dividing by 4. But I didn't because of the range. Cool. Yep. If you want to, but the problem is then you're going to be narrowing your range of data. So long as the range of data is 0.3, it will average just fine. Even if you eliminate a second one and you get your range to be smaller, you're then compromising on potential accuracy because maybe you eliminated a number that was actually closer to the true value. Does that make sense? So if you're not sure and you're like, oh, I don't know if like this number seems really low compared to the other ones, you could always, like I said, do another titration and get an idea of where, like if it's upper or lower range if you're not sure about that one. This one's likely the outlier, but you can do another titration just to double check it. Yeah. Huh?
If this one is wrong,
yeah.
Then we have to do
So let me show you what you're going to do for Achieve Merit Excellence. So if you guys look on your resource sheet, you guys have this, assessment requirements. All right. So first thing to kind of note is where the achieve stuff. So there's lots of ways you can get the achieved to pass, so you don't have to stress too much. The first one is calculating the concentration of the standard solution. So when I say concentration of standard solution, I'm saying getting up to this point here, that would be an achieved. You can mug up the rest of it and you'll still pass. That nice? That's nice. All right. Or incorrectly calculates the first half of the calculations, but uses a mistaken calculation correctly to calculate the concentration of the primary solution. So let's say you made an error somewhere and that error carried through. I could still give you an achieved. The other thing I can give you an achieved for is if, say, for example, you completely muck this up, I can still look at part A, and I can check if you've done a correct dilution for part A. So lots of choices. So if you've already done well in part A, I can still use that for an achieved. Or in part D, you do a conversion correctly. So basically, give it a go. You're likely to get an achieved when you give it a go. Okay? For the merit, you actually get 2 chances for that. The first thing is that you need to do this calculation correctly either in part B or in part C. So if you completely bomb this part B, you can still get it in part C. It's the good news. And you can still get a max grade of a merit. If you are aiming for excellence, you need to have the calculations correct for both B and C. So what I'm going to do when I'm marking these guys is I will mark it up to excellence looking for the significant figures and things like that. But be mindful you need to pass it twice. B and C. Cool. But the good news is the part C calculations are more or less exactly the same. All right. Questions, concerns, comments? It's not too bad, I don't think. All right. I will make sure I scan that. I'll pass out some practice questions, and then I'll talk about what we're doing for the rest of the lesson.